NextGen RF Design is an experienced engineering services provider, specializing in wireless and RF product development. We've teamed up with Richardson RFPD and Analog Devices to create a narrowband receiver demonstration for the ADRV9002. This demonstration uses the Analog Devices ADRV9002 RFIC and HMC 8410 low noise amplifier to receive P25 public safety radio signals from a nearby radio system. The ADRV9002 samples the received signal at a low IF, filters the samples in the digital domain, and provides I and Q samples to an FPGA, where they are processed and streamed over a USB to a PC. The PC is running a software-defined radio application, which decodes the trunk control signal so that we can identify users and groups, and also provides an audio codec so that we can listen in. At the heart of the demonstration is the ADRV9002 evaluation board. The ADRV9002 NP W1 and W2 are FMC radio cards for the ADRV9002 highly integrated RF transceiver. It offers dual-channel transmitters and dual-channel receivers, integrated synthesizers, and digital signal processing functions. The ADRV9002 operates from 30 MHz to 6 GHz and is capable of supporting both narrowband and wideband standards up to 40 MHz of bandwidth on both receive and transmit. This demo uses the internal synthesizers and external signal generator as the reference clock to generate the LO source. The HMC 8410 LNA demo board is used to optimize gain and noise figure. The transceiver evaluation software, or TESS, is provided by Analog Devices and was critical for ensuring correct configuration of the ADRV9002. For the P25 demo, a custom receive configuration was generated using TESS. TESS was used to generate the sample code for configuration of the ADRV9002. This code was compiled as part of the custom baseband processor application that streamed the IQ data to the PC. The ZC706 evaluation platform is used to interface to the ADRV9002. The XC7Z045 SoC provides baseband processing and communication to the PC. A custom HDL interface was developed to interface to the ADRV9002 receivers and configuration registers. The received IQ samples were streamed to memory using a DMA. The Cortex-A9 processor managed DMA interrupts and streamed the IQ samples over USB. A custom USB driver was used to interface to the PC. The baseband processor Cortex-A9 is used to configure the ADRV9002, process USB packets, and manage the DMA for IQ samples. The software used to configure and control the ADRV9002 is generated from TESS and used without modification. As IQ samples are streamed to memory, the processor ensures they are routed to the USB controller. There are many software applications available in the open domain that are useful for decoding radio signals from IQ samples provided over USB. SDR Trunk has the decoders we want and is designed for the use of trunk signals. The application is a Java-based application, can be easily transferred to any OS running Java. SDR Trunk can simultaneously decode all channels within the tunable bandwidth of the ADRV9002, or can be configured to automatically create and tune individual traffic channels when decoding the control channel. To make the application work for our demo, we modified the SDR Trunk source code to include our own custom device type, and use the SDK to initialize the hardware. The IQ stream from the FPGA is formatted for the application to use in its native form, so the rest of the application is largely untouched. The ADRV9002 is configured as a wideband receiver, sampling up to 40 MHz of the UHF spectrum used for police and fire safety. The sampled IQ data is converted into multiple narrowband 12.5 kHz channels. The following shows the wideband spectrum along with active narrowband 12.5 kHz signals. The PC is set up to continuously monitor the control channel of a nearby trunk system. When the users become active, the software decodes them and plays the audio. The wide bandwidth of the ADRV9002 allows for multiple users to be decoded simultaneously while providing the performance required for a narrowband system. Let's listen in.
13 towards her. 13. I have a VIN to try when you're ready.
Good.
1, F Frank, T Tom, Z Zebra, X X-ray, 8, William, 0, William, King Boy, 10609.
10-4, where do you want me with this pin?
For optimal performance, the ADRV9002 can be configured to receive a single 12.5 kHz channel with both DSP and analog filtering. Further, the high dynamic range receiver can coexist with adjacent channels by having over 150 dB per hertz dynamic range without using AGC. And to avoid DC offset issues in direct conversion receiver architectures, a low IF mode is possible for narrowband signals.
To go along with the ADRV9002 eval platform, several of Richardson RFPD's partners have developed platforms that utilize the ADRV9002 and could reduce the development time of your project.
While the P25 demonstration highlights the narrowband performance of the ADRV9002, it is capable of so much more. That's why NextGen RF Design is developing a System on a Module, or SOM, to create a user-friendly hardware solution. This will enable users to quickly develop and evaluate a variety of radio applications. The BytePipe 9002 includes a high-performance onboard Xilinx UltraScale Plus FPGA. The small form factor makes the SOM suitable for end product integration, enabling faster time to market and lowering non-recurring engineering costs. The following models show the small form factor of the highly integrated BytePipe 9002 RF SOM. A custom RF shield provides superior RF isolation along with a heatsink for the baseband processors. The 2 transmit ports and 4 receive ports are optionally accessible either through topside U.FL connectors or bottom side SMP mini connectors. The SMP mini connectors can be used with SMP RF adapters for board-to-board connection of the transmit and receive ports. A 120-pin high-speed digital board-to-board connector allows for communication with the host board. The SOM hardware architecture integrates all the common hardware elements of a software-defined radio platform. At the heart of the SOM is an ADRV9002 RFIC and UltraScale Plus SoC. The ADRV9002 supports virtually any RF communication standard from narrowband to wideband with up to 40 MHz of bandwidth. The ADRV9002 has 2 transmitters, 2 receivers, and 2 integrated synthesizers supporting a range of FDD and TDD modes. Each receiver can be switched between 2 50-ohm 30 MHz to 6 GHz receive ports, allowing for optimal tuning or supporting one of the observation receive paths for digital predistortion and transmitter power monitoring. The 2 transmit ports support 30 MHz to 6 GHz with up to 6 dBm of continuous output power. The UltraScale Plus system on a chip provides the optimal baseband processing capability to complement the ADRV9002. It includes up to 4 Cortex A53 processors, 2 real-time Cortex R5 processors, and an ARM Mali graphics processor. The 7 processor cores coupled with programmable logic and DSP hardware slices offer exceptional baseband processing capability. Up to 2 GB of low-power DDR4 and 8 GB of eMMC memory provides high-speed memory access. The SOM interconnect supports several high-speed flexible interfaces to the host processor. Up to 4 high-speed serial transceiver ports can be configured to support a combination of DisplayPort, PCI Express, USB 3, SATA, or the standard gigabit media independent interface. In addition to the high-speed transceivers, gigabit Ethernet and USB 2 are supported. Up to 8 high-speed LVDS signals or 16 single-ended I/O allow for custom communications to the programmable logic. In addition to high-speed interfaces, up to 26 I/O can be configured as GPIO, SPI, I2C, or CAN, operating at 1.8, 2.5, or 3.3 volts. For additional storage or for booting, a SD card interface is also supported through the SOM interconnect. The SOM is powered by a single 5-volt supply through the SOM interconnect. all the necessary digital and analog regulators are retained on the SOM, minimizing host requirements. In addition to the 5-volt power supply, the host provides a reference supply of 1.8, 2.5, or 3.3 volts for the communication interface between the SOM and host. To power our SOM, we have selected the Xilinx UltraScale Plus family of devices. This pairs the FPGA logic with a dedicated real-time dual-core ARM Cortex-R5 processor for DSP and radio management functions. While a separate multi-core ARM Cortex-A53 handles all the application processing, the SOM supports both CG and EG devices. The EG devices support an ARM graphics processor, which can be used for surveillance, embedded vision, and multimedia applications. And since the UltraScale Plus family uses a 16 nanometer process, it has a system-level performance of up to 5x higher per watt than the Zinc 7000 SoCs. To facilitate development onto a customer platform, we have developed a breakout assembly to give access to high-speed interfaces. The design files of the breakout board can be leveraged for hardware design of the end product. The following slides outline the BytePipe 9002 software provided by NextGen RF Design. Along with hardware, NextGen RF Design provides a software ecosystem to enable developers to quickly integrate the SOM into their product. This ecosystem is built around enabling the customer by providing board support packages and reference designs. The user can use pre-built portions of the system or customize for their needs. The BSP supports Linux, RTOS, and bare metal operating systems with application examples for each. The software is broken into 3 layers: application, board support package, and hardware platform. The hardware platform is generated based on the HDL and enabled peripherals within the UltraScale Plus processors. Once a hardware platform has been created using HDL tools, a board support package is generated. The BSP includes all the necessary C drivers for interacting with the hardware. The application layer resides above the BSP and can be as simple as a single layer Hello World application or a full communication stack with MAC, networking, and application layers. The design files provided by NextGen RF Design are separated into folders based on the corresponding layer. The hardware platform design files are in the HWP folder. These can be used as is or generated based on custom HDL. The HDL folder includes the design files for generating a hardware platform. It includes common HDL IP, HDL projects, and scripts for generating the projects. To create a custom hardware platform or to modify an existing hardware platform, the HDL must first be modified using Vivado. Here we have the Vivado design tool. An existing project can be created by executing the corresponding script. First, the directory must be changed and then the script executed. Vivado will create and build the project based on the source files and applicable IP. When the build script is executed, Vivado will start creating the block design. Once the block design is created, Vivado will synthesize and implement the design. This design consists of an UltraScale Plus processing system and a single ADRV9002 receive port. The received IQ data is streamed to memory using the DMA and can be further processed by the UltraScale Plus processors. A custom SPI module provides the processors with direct access to the ADRV9002 registers. This is a baseline design demonstrating only one receive path of the ADRV9002. Additional receiver and transmit paths can be added from NextGen RF's catalog, which includes several IP blocks such as the ADRV9002 IP and others. Once finished, the hardware design can be exported and later used to create a hardware platform. The software development kit is used to import the hardware platform and create both the BSP and application. To get started, a workspace must be created and projects added to it. A hardware platform can be created based on the hardware exported from Vivado. This is done by referencing the hardware definition file within the Vivado project folder. The hardware platform, once generated, includes the code for configuring and initializing the processors. It also includes the memory-mapped hardware addresses and registers. A board support package can be created based on the hardware platform. The board support package includes all the code for interfacing to a specific hardware platform. To create a board support package, the hardware platform and operating system must be selected. The user can then select additional support libraries as needed. These libraries include Xilinx libraries, third-party libraries, and NGRF libraries. The libraries implement specific algorithms or pieces of functionality and are typically not based on specific hardware platforms. Once the BSP is created, all the source code and libraries are imported to the BSP project. A system file provides documentation and examples for each driver. The examples are fully executable reference designs demonstrating the driver's functionality and performance. The user can decide to create custom hardware platforms and board support packages, or use pre-built examples provided by Next-Gen RF Design. Here we are importing an existing BSP into the workspace. This BSP uses a real-time operating system. Next, we are going to import a simple NGRF CLI application that configures the ADRV9002 and allows for the user to control from a command line interface. Once built, the application can be downloaded and run on the target. If we connect using the command line, you will see the application initialize and configure the ADRV9002. The user then has the ability to send commands to control the radio. Several additional application examples are provided, including the Spectrum Analyzer. This application demonstrates various peripherals, including the ADRV9002, along with FFT signal processing and video processing within the programmable logic. Next-Gen RF Design provides a library for interfacing to MATLAB. This example shows MATLAB processing IQ samples from the SOM and performing carrier recovery. Next-Gen RF provides several examples for using System Generator and Simulink for the design and simulation of signal processing within the FPGA programmable logic.